everybody. Welcome to the lesson on repeated measures ANOVA. So repeated measures ANOVA is done for the same purpose as the paired t-test, except we can run the repeated measures ANOVA when we have more than two measures. So with the paired t-test, we could only run that with two measures. And technically, we can run the repeated measures ANOVA when there are only two. But we usually don't, because the repeated measures ANOVA doesn't have the one-tailed versus two-tailed option, whereas the paired t-test does. So, so our null hypothesis, and we usually don't state this, like we do some of the other tests we run. We usually don't spell this out, but the null hypothesis is that all the measures are equal. And the alternative hypothesis is that at least one of the measures differs. In this test, our independent variable is which of the measures we're looking at, the first, the second, the third one. And these don't have to occur across time. Sometimes this is just, different measures. And we'll see an example of that in just a minute. And the dependent variable is the value of that measurement. So let's look at a couple of examples. A lot of times we will want to look at changes over time. So I think an example I gave the other day was if you've got people doing performance on a test at the beginning of the semester, at midterm, and then at the final exam time. That would be three different measures, and we could compare those using repeated measures ANOVA. We could also look at something like typing speed on different kinds of keyboards. We could test somebody's typing speed on, I don't know what the different kinds of keyboards are, but you've all seen them. Say we get 4 different kinds. They've got some ergonomic ones and, whatever. But so we could test people's typing speeds and see if they're different. The example I want to look at in today's lesson is this house data set, which I think we've looked at before. We've got three variables here I want to compare to each other. We've got the sales price of a house, and all of these are in thousands, so 259 means $259,000. So you've got the actual sales price, the appraised value, and that's done by a real estate appraiser, usually right before a house is sold or refinanced or something. And then the assessed value, which is for tax purposes. That's usually done by the county for purposes of deciding how much taxes you have to pay per year on the house. So we've got these three measures, and we want to know how close are they to each other. Basically how well does assessed value do at predicting the sales price, for example. So to run our repeated measures ANOVA, we're going to go to Analyze, General Linear Model, and then Repeated Measures. So that's Analyze, General Linear Model, Repeated Measures. And we usually want to give this factor some kind of descriptive name, like if time is a factor, you could put time as your factor name. I can't honestly think of a good name here, so I'm just going to call this source of the measurement. And we've got 3 levels: the sales price, the appraised value, and the assessed value. So in this case, we've got 3 levels. So we're going to click Add, and then Define. Once we click Define, we just have to move our 3 variables over here. So I'm going to put these in alphabetical order just because you don't have to do that. If you've got your data in a time order, you want to put it in time order. So you want to put, like, if there's one example where it's like 2000, 2010, 2015, you want to put those in order from according to time. Otherwise, it doesn't really matter. And just because we're going to be looking at a few things later, let's go ahead and do options. And we are going to want to see descriptive statistics, estimates of effect size, and for one of our assumptions, homogeneity tests. And then I also want to look at a profile plot. So under plots, just take your factor and move it to the horizontal axis. And then click continue. Oops, click add first. And then click continue. All right, and once you've got all that, click OK. And we get our output. And I've copied this over here so we can talk about it. And I can draw on it. So starting with our profile plot, this is why I wanted to put these in an order that I would remember. Because here on the profile plot, they don't tell you, they just label 1, 2, and 3 without any more information. So that's a little frustrating. And with the way this y-axis is scaled, it can be a little bit hard to tell if there are differences. So they zoomed in, which kind of exaggerates the differences. Just psychologically, that's if you look at, well, this is a little bit sidetracked, but not much. If we were to look at that graph where the y-axis was at 0, it would probably look a lot more like this. So anyway, when you zoom in, it gets a little bit harder to see, what's going on there. If you're doing a different example where time is your factor, this can be really useful to see first, second, third. But be careful if your time intervals are not all equal. That one example I mentioned, we've got year 2000, 2010, 2015, 16, 17, 18. Those times are not all equal intervals, so you'd want to be really careful with that. Let's look at our descriptive statistics. This is telling us that the appraised value is the highest, which does not surprise me based on my experience with appraised real estate appraising. You guys may not know, but I actually, for a very brief period of time, was a real estate appraiser. And yeah, I'll tell you about that sometime. Anyway, so the appraised value is the highest, followed by the sales price, and then the assessed value is the lowest. All right, let's talk about assumptions before we actually run the test. That's because there's one assumption that we're going to talk about here, and it's a pretty important one. And it's called spherocity. It looks like it ought to be sphericity, but I've always heard it pronounced spherocity. Spherocity is an extension of the homogeneity of variances assumption. But it's in 3 or more dimensions because we've got 3 or more groups now. So if basically spherocity will hold if the differences across all of the groups in terms of variances, if the variances across groups are all about the same. Otherwise, spherocity will be violated. We're going to evaluate spherocity using something called Mauchly's test. And for Mauchly's test, the null hypothesis is that spherocity is not violated. And the alternative hypothesis is that spherocity is violated. That was supposed to be ditto marks, but my mouse pen is not cooperating. So a small p-value would mean that spherocity would be violated. So if we look at Mauchly's test here, we see a p-value of 0.246. This p-value on spherocity is large. Therefore, spherocity does not appear to be violated, or the assumption of spherocity does, how do we say this? So there is not sufficient evidence to conclude that spherocity has been violated. Okay. So it's not violated significantly. I'm having some trouble with my mouse pen here. Sorry about that. I'll fix that for giving it to you later. So we need to know if spherocity has been violated before we can run our main test. That's because we've got 2 options here for our test statistic and p-value. And you see here they're the same in this case, and they often will be. But if the spherocity assumption is violated, we're going to use the Greenhouse-Geiser row for the test statistic, p-value, and partial eta squared. Otherwise, if it's not, then we're going to use spherocity assumed. Okay, so you're going to use one of these 2. Like I said, in this case, it's the same, and it often will be, but in the cases where it's not, that's how you know which one to use. So in this case, we've got an F of 66.566. We've got a P less than 0.001. And we've got a partial eta squared of 0.711. And we haven't talked about effect size yet, but it's the same. This partial eta squared is the same as what we had before. This is the same sort of attempt at getting at the coefficient of determination, the R-squared value. Basically, we just need to state it. So the effect size, we just talked about the partial eta squared. Now let's talk about post hoc tests. Post hoc tests, if you remember, are when you know there's a difference across groups and you want to figure out, you want to look at those comparisons pairwise. So we know that for our data, we know that not all three of these values are the same. Sales price, appraised value, and assessed value. They're not all the same. So the post hoc tests are going to tell us which pairs of those are different from each other. So to look at this, we're going to go back to our repeated measures. And we don't have to redo this, just click define. And surprisingly, to get our post hoc tests, we're not looking under post hoc this time. This time we're looking under EM means. This is estimated marginal means. And I actually haven't looked under post hoc to see what's going on over here, but for some reason this just doesn't work. This isn't showing us a factor. But EM means will give us what we want. So don't do the overall, we just want the source because that's our factor. And we're going to move this over here to display means for. And we want to compare the main effects. We have three options here. And as I put over here, if spherocity has been violated, we're going to use the Bonferroni option here. Otherwise, we're going to use this LSD none. LSD means least significant difference. Doesn't mean any substance thing. So we're going to use the least significant difference. Otherwise, the Bonferroni. Click continue. Click OK. And then if you scroll down, you see the pairwise comparisons. That's what we want. So I copied this over here so we could talk about it. And if we look down here at the SIG column, this is telling us that, let's see, I wrote 1, 2, and 3, so we know what's what. It looks like at the 0.05 level, there's a difference between the appraised value and the sales price. And both of the other comparisons are significant at the 0.001 level. So between appraised value and assessed value, and between assessed value and sales price. Those are significant at the 0.001 level. So now let's talk about the write-up. The write-up is going to be basically the same thing we've seen before, where you're going to talk about a sentence of, you're going to do a sentence explaining what test you ran and why, what you were looking for. Then you're going to evaluate assumptions. You're going to state descriptive statistics. You're going to talk about the results of your test. And then, if applicable, you're going to run post hoc tests. And you're only going to run post hoc tests just like we've been doing if the main test is significant. Shrink this a little bit so we can read it. All right, so here's the write-up that I created. Yours may be a little different, and that's okay as long as you use correct statistical language. And you include everything you need to include. So we ran a repeated measures Anova to test for a significant difference in 3 methods of measuring the value of a home. And those methods were sales price, assessed value, and appraised value. So that's our sentence to summarize what we're doing. Next, let's evaluate assumptions. Mauchly's test did not show a violation of the spherocity assumption. We put the p-value there. Therefore, we ran the test using the spherocity assumed option. And then here's the results of the test. It showed a significant difference. We state our test statistic, p-value, and effect size in the different methods. And then I'm going to talk about descriptive statistics and post-hoc tests. Descriptive statistics showed appraised value with the highest mean, and I stated the mean and standard deviation, followed by sales price. Here's the mean and standard deviation, and the assessed value. And I stated the mean and standard deviation. And then post-hoc tests showed a significant difference between sales price and assessed value at the 0.05 level, because this p-value is 0.012. And this is a little bit of an awkward way to phrase this. I wasn't thrilled about this. Maybe you guys can come up with a better way to say this. And between both other pairs at the 0.001 level. So between 1 and 2, so between appraised value and assessed value at the 0.001 level, and between assessed value and sales price, so between 2 and 3. All right, so that's all there is to this lesson. I hope this is helpful, and you know, as always, please let me know if you have any questions.